So hello, this is Andrew Lenart, and this is my lab 3, magnetic moment of a bar magnet. So what we used in this lab was a bar magnet, tape, and a ruler, and also software such as an app Teslameter to record the magnetic field from the phone's perspective, and GlowScript. We wanted to determine the magnetic moment of our magnet by recording the magnetic field at several locations. Then we also wanted to create a simulation observing the magnetic field at several locations using that data. So the procedure. We first want to zero out the sensor in the X. So we wanted to find an orientation of the phone such that the X component of the magnetic field would be close to 0. And this was done so that our recordings would be more accurate. Next, we also wanted to locate the magnetic sensor on the phone. So what we did is, as seen in the photo, we placed the magnet perpendicular to the phone and saw where the X component of the field was greatest. And that we placed tape right there. And then similarly, we turned the phone 90 degrees, we did the same procedure and placed tape where it was greatest in the X. And where those two pieces of tape intersect is where the magnetic sensor is. So what we did is we recorded the distance from the sensor for several z components of the magnetic field. So for example, here we wanted 2 times 10 to the negative fifth Tesla. And we wanted to see how far away our magnet had to be in order to give us that value. And we repeated this process for different values. So as you can see here, 7 times 10 to the negative fifth, 1.2 times 10 to the negative fourth, etc. And we recorded these values onto the spreadsheet. Then we did a similar setup this time, but this time we placed the magnet a distance away in the x and the y so that the x component and the y component distance was equal, so that it gave us a 45-degree angle. And this as well, we entered it into the spreadsheet. So the starting code conditions. So what do we need to make the code? So we wanted a code to model the field of the magnet at different distances, but we need some starting conditions. Specifically, we need the magnetic dipole moment of the magnet. And we can derive this using the data we collected. So we plotted a graph of ln bx versus ln r. And in the next slide, I will show you how to use that information to go over the dipole moment. So using that graph, we found that n, so as you can see here, it's n is the slope of the line, and it was -3, about -3 basically. And then ln k was negative 14.568, and when you solve that, it gives us k equals 4.712, 10 to the negative 7th. So here we know that kr to the n is equal to mu naught over 4 pi times 2 magnetic dipole moment over r cubed. And we know this equation on the right to be the equation of a magnet parallel on axis with a location. So because n is -3, we have r to -3 here and basically r to -3 here, so we cancel those out. And we find that k is equal to mu naught over 4 pi times 2 magnetic dipole moment. And basically we rearrange this equation to find that the dipole moment is mu naught 2 over 4 pi k is 1 over mu, 1 over the dipole moment, and basically the dipole moment is, once you solve it, is 2.356. Now that we found that data, we used an equation for a magnetic field to write a function that calculates the field of the magnet, as can be seen here. We have the r magnitude, r hat, and we enter that into the equation here. And then we pick certain locations. So we want to do two locations on axis, 4 locations perpendicular, and 1 location at 45 degrees. So basically we set the locations here, and we use this function to calculate the magnetic field at those locations. So what are the results? As you can see here, these 4 blue lines are at perpendicular locations, and the 2 orange are at parallel location on axis. As you can see here, the orange lines are considerably stronger than the blue ones. And if you look here in the smaller corner, that's the magnetic field at 45 degrees away. Now, there's something very unusual we found about the data, that in the experiment, we got the magnetic field at 45 degrees to be 1.6 times 10 to the negative 4 Teslas. While in the code, it said it was 1.014 times 10 to the negative 5th Tesla. And the error seems very weird because it's by a power of 10, so we may have made an error somewhere, or they were extremely inaccurate. We're not really sure where the error came from. But now, concluding notes. So what if I hadn't zeroed out the sensor at the start? So all of our answers would have had a component of the Earth's magnetic field affect the answers. This can be visualized as in this case, the Earth's magnetic field would not be perfect on the y-axis, and therefore it would have a component in the x, the field we are measuring for most of our experiment. And it will also have a bit in the z as well, depending how it was oriented. Now, what if we were to stick two identical it would also affect where the magnet is on the phone, like where we locate it on the phone. What if we were to stick two identical magnets together end to end and run the experiment again? Now, I personally believe that expect the magnetic field to roughly double for each location. I believe this is because it seems that as this seems the same as adding double the charge to a dipole, like a normal electric dipole. However, in this case, we would be doubling the number of magnets. And in the electric dipole case, you'd be doubling the electric field. So I believe in this case, you'd be doubling the magnetic field. So thank you very much. My name is Andrew Lenart, and this has been my lab.